This engineer's nightmare first happened on Jet in March 1984. As the plasma hit the top of the vessel, sparks flashed around the structure and the 100-ton torus lifted 1 centimetre into the air, then fell back down. As temperatures rise in the plasma donut, ways will have to be found of avoiding major instabilities. In the winter of 1989, regulars at a secluded Oxfordshire inn called the Machine Man might have noticed a small group who sat each lunchtime poring over plans and calculations. Among them were Tom Todd and theoretical physicist Alan Sykes, who'd been working at Culham on plasma configurations. Both were excited by a new American proposal for a tokamak design that should reduce the instability problem.
Because you're going to have to up the currents and the internal flux, of course, to meet...
Since all were employed on other projects, they couldn't officially devote any time to the new idea. So, convening in the pub, they plotted how to recycle parts from Zeta and other past experiments to build a tokamak shaped not like a donut, but almost spherical, like an apple, with the core removed. That idea became START. The small, tight aspect ratio tokamak at Culham has now attracted researchers from Russia, Brazil, and even from the American laboratory, which thought up the idea, but never built it.
START has been remarkably successful, far better than we ever thought. Whenever you normally construct a new concept, like START is, you find that there's new instabilities that come and get you never thought of. The plasma may be impure and very cold. But right from the beginning, we've had remarkable success with START. We've got very hot temperatures, 10 million degrees centigrade, which is very high for such a small machine. And the plasmas have very good positional stability. They just form around the center column until they naturally decay away. And one unexpected feature is we never see the major disruption, which is such a bad feature of modern tokamaks.
High-speed photography shows how START's plasma forms a very stable D-shaped ring around the core of the spherical vessel.
The mainstream at the moment is the right way to go to get something that you can study burning plasmas in. But to get economic fusion, we have to explore many avenues. And the START machine at Culham is just one avenue that we think is very successful. But in other laboratories in other countries, I'm sure people are studying alternative approaches, perhaps just the extreme to START, rather than very tight plasmas, very slack plasmas like the bicycle inner tubes, because there are some features of those that could be explored yet. So it is my hope that someone somewhere will come up with the breakthrough that will make fusion power much more readily achievable, and it might be us, who knows.
But after years of trying to achieve fusion power, the biggest hurdle facing its supporters may now be to persuade governments and critics that the end really is in sight.
If money were unlimited, there might be a good case for carrying on with fusion research at this level. But money is not unlimited. Yes, you need the flexibility for new technologies as they come along. And certainly, if money were freed up, for example, from nuclear weapons, then it might be feasible to use that on nuclear fusion. But my big concern is that unless we start acting and really moving away from fossils in the next 20 years, we're not going to have the choices available to us in the year 2050 to plump for fusion or not, because we'll be already into such environmental damage and climate change that we won't have choices anymore.
But the choices are not only fusion versus renewables. Fusion itself has pursued many competing paths. And some wonder if it is now time for a more aggressive commitment to one technology.
It's the question that scientists are plagued with continuously. The motivation for being conservative is based on the fact that from a professional and personal perspective, scientists do not like to fail. And when you are aggressive, you significantly increase the probability of failure, although when you succeed, you move ahead much faster. but I would be willing to make an agreement. If you give us more money, then we will be more aggressive, rather than assuming parallel approaches to minimize the risk of failure. We would be willing to select and take fewer approaches and go at higher risk, but then the government would have to understand that in doing so, we think, we are quite convinced we could get them the end result sooner. But if one of those approaches should fail, they should not hold us responsible as saying, well, we could do it, but it didn't work.
One of the most poignant reminders of the scale of this gamble and of the risks it carries is the Mirror Fusion Test Facility in California. Completed in 1986, it cost $372 million. Guests from around the world had already been invited to a grand opening ceremony when the US government decided that no success was likely and withdrew funding. The machine has never been used.
Ultimately, you have to decide whether this is a very interesting exercise in particle physics and plasma physics, or it's a practical alternative to fossil fuel energy. Now, if it's supposed to be a practical alternative, then obviously socioeconomic considerations have to be brought in. What sort of costs are likely to be the case? What sort of design and technologies and radioactive waste and other problems? If you don't bring those in early enough into the design process, you may end up spending a great deal of money, whereby if you'd asked those simple questions very early on, you might have decided that, well, it is an interesting experiment, but in the time scale that's realistic for us, and where we have needs for a return from our energy research, that it's not an option worth spending tens of billions of dollars on.
It may be true that we won't, in our own lifetime, see much benefit from this, but I think the way that things are going in 30 or 40 years, we should see fusion power becoming available. There may be other forms of power become available by then. But if not, the world will be in a bit of a mess the way things are going, and I think it's very important to pursue fusion research.
I personally, as many of my fusion colleagues, are motivated by the dream, the vision of that, what we work on. When we make it happen, will it profoundly change the future of mankind? Now, I don't tell myself that every day, but once in a while, when someone asks me a question, I realize that, that's what I'm involved in, and that's okay. I mean, it's nice to be able to do that.